Hello, welcome back to Math 152. Today we are going to look at two more examples from section 7.3. So let's get to it. The first example involves the evaluations of a definite integral of this type. So one way to solve this problem is to find the antiderivative first. And then once you found the antiderivative, you're going to substitute x equal to 0 and x equal to 2 over 3 into that antiderivative and obtain the answer. Now, that is definitely a way you can try, but for integral, which require you to use substitutions, or like in this case, trigonometric substitutions, it is easier to not to do that. And I'm going to show you what I mean and that particular alternative in a minute. But now let's just concentrate on this integral of this type. And we know that in the book, if it says that you run into expression that looks like this, we should try x equal to a sine theta with this a. So you might want to start with x equals to 2 sine theta, and immediately if you try this, you will see that you'll run into trouble because all the factorizations and things as nice would not work in this case because this is designed to deal with 1x squared, but you don't have 1x squared, you have 9x squared. So one way to deal with it is to do some algebra to clear up all this complications. So in order to have a 1x squared, in order to get rid of the 9 and have a 1x squared, you should choose to factor out the 9 so that you have 4 over 9 minus x squared. And because of square root of 9 is 3, so this is nothing but this. And 4 over 9 can be written as 2 over 3 squared, and then minus x squared. And then from here, you will have the form of a squared minus x squared. And then now, if you substitute x equals to 2 over 3 sine theta, and you will see that this will work. Okay, so the substitutions that require you to do is to take x equals to 2 over 3 sine theta, and then the dx will be 2 over 3 cosine d theta. And all these substitutions, once you put all this thing in, and you can see that nice things started to happen. The 9 and the 9 cancel out. And the 4 and the 4, which you can see right here, can be factored out. And then it left you with 1 minus sine squared theta, which is cosine squared theta. So this whole thing, once you clean up all these constants, you will get absolute value of cosine theta with cosine theta. And you will turn this integral into the integral of cosine squared theta. Now, this is the magic of using the right substitutions. So the main things for this substitution to work is to try to exploit this kind of relationships so that we can get things simplified to a stage where it is manageable. For example, this particular integral. The way to solve this integral, we learned it in section 7.2, which you have to kind of invoke the double angle formula for cosine. And then once we get into that stage, we get this. And then everyone should know how to integrate 1, which gives you theta. And when you integrate cosine 2 theta, you will have this. And remember, if you want to find the antiderivative in x, this is not the final answers. You will have to write everything in x. And the way to do it is to bring in this triangle. So we know that the sine theta is 3x over 2. So this is 3x over 2. And it is easy to find what is the length of this side. Then you will get this terms right here. And because we have theta, not 2 theta, so you will have to use this formula, which is sine 2 theta equals to 2 sine theta cosine theta to, and then since we have 1 over 2, so you get these expressions. And then now we are in business because sine theta is 3 over 2, so that's the 3 over 2. And then with this triangle, you can figure out cosine theta also. That's the cosine theta. And because sine theta is 3 over 2, the theta will be the inverse of the inverse of 3 over 2x, which is what you found here. That will be finally your antiderivative. So one way to solve this problem is to find the antiderivative like this. And then for the definite integral, you will just have to substitute the x equal to 0 and x equal to 2 or 3 into your antiderivative and do these computations to obtain pi over 3. Now, the second method, which I'm going to tell you in a minute, is that we can actually bypass the entire triangle stuff. We don't have to write everything in terms of x. What you can do is to figure out, once you have this x equal to 0, what is the corresponding theta for x equal to 0? So you want to write everything in terms of theta. So when x is equal to 2 over 3, what is the corresponding theta for this particular x? So remember, for this kind of substitution to work, our theta is actually chosen in this range because we will have to invert it and so on and so forth. So in order to make things work, so our theta is between negative pi over 2 and pi over 2. So when you choose, when x equal to 0, the theta, which is in this range, which solve these equations, will be theta equal to 0. And your x, when it is 2 over 3, the theta, which is in this range that will solve these equations, is theta equal to pi over 2. So the corresponding, for the x equal to 0 will now convert to theta equal to 0. And the x, which is equal to 2 over 3, will now convert to pi over 2 in theta. So with this, all this integration is the same as before. But the key difference is that once you integrated this, you do not have to go back all the way to the x, so you don't need to draw this triangle because we don't need to know the x. All this is already in terms of theta, so here you can immediately substitute the theta equal to 0 and theta equal to pi over 2 into these expressions and do these computations and obtain pi over 3. So this is easier in the sense that once you have done this analysis, you actually do not have to go back to the triangle. So you don't have to write everything in terms of x. So that is an alternative which you should try for your web assignment questions. We do have a lot of integral which involve definite integral. Right, so this is one alternative. So let's look at the second example. So the second example is something that's a little bit weird because if you look at the textbooks, for trigonometric substitutions, we always kind of like try to do trigonometric substitution on expression that looks like this or expression that looks like this and so on and so forth. But obviously for this problem right here, we don't see that because this is not a complete square of something. This is x and then you have x squared. But we should be able to turn this thing into something that looks like this by completing the square. So we use completing the square a lot. So if you forgot how to do these completing the square, please make sure you review it. So if you complete the square, you will see that these expressions right here, x minus x squared, is actually 1 over 4 minus x minus 1 over 2 bracket square. So you can write this as this. Now, the second weird thing about this question is that if you look at the expressions that we are familiar with, we are always doing expressions that looks like this, but we never do expressions that looks like this. Well, it's actually not going to be a problem. So maybe if you want to think of it, you should think of it like a squared minus some kind of box square. So here, your box here in this case is x minus 1 over 2. And the thing in the box is the one that you want to substitute as a sine theta. So in our case, the x minus 2 should set to 1 over 2 sine theta because your a here is actually 1 over 2 because 1 over 2 square gives you the 1 over 4. So let's try to do the substitutions. Now the dx is going to be the same as 1 over 2 cosine theta d theta. Because negative 1 over 2, if you differentiate that, it's just going to give you a 0. So here, the thing says in the box is going to be this expression here. So that's the substitution that you should try. Okay, so even though we write x squared here, next time if you have trouble with this, you can just think of it like some kind of box square, and the box will be the a sine theta in this case. All right, so you will see that once you have done these substitutions, nothing actually is different. So everything is still the same. All this thing is the same. You will have the 1 over 4 so that you can factor out. And then you have the square root of 1 minus sine squared theta, which can change into this. Everything works out pretty well. And we don't have to worry about the x minus 1 over 2 business at all right now. So you turns into this. And this is the same question as the example that we have before. You have to use the double angle formulas to simplify it. And then you collect the constant terms, and then you integrate this to have this, so on and so forth. Now, if you want to find the antiderivative in terms of x, this is the only time you have to look at this expression one more again. So you will be like x minus 1 over 2 is equals to 1 over 2 sine theta. Therefore, your sine theta will be the ratio of x minus 1 over 2 over 1 over 2. So you will have to write x minus 1 over 2 over 1 over 2. And then this side here will be this. And this is the only time you come back to these substitutions. And then you will have to do the same thing to figure out what is the sine theta and cosine theta. But once we have this, all these things are easy to compute. You can also do a little bit of algebra to change all this into this, because no one really like to see things like that. So you can kind of write the equivalent form, which is 2x minus 1. So you change all this into that. So this is the entire derivative. So once you have the entire derivative, now you can substitute the 1 and 0 into the entire derivative, do the computations, and then you will get these answers. Now, same thing as before, another alternative is not to go all the way to the triangle. In fact, if you can figure out what is the corresponding theta for this x equal to 0, because we are integrating from 0 to 1. So if you can find the corresponding theta for x equal to 0 and the corresponding theta for x equal to 1, in this case, our theta is actually negative pi over 2, and theta is pi over 2. Remember that we want to find our theta in this range. So the integral will change into this. So now everything is in terms of theta. So once you get to this stage here, as usual, as the one you've seen from the first example, you can just substitute the pi over 2 and negative pi over 2 into this expression. As you can also see that we don't really have to turn into the 2 sine theta, cosine theta, because we can you have theta equals to pi over 2. That is no problem whatsoever to compute what is 2 theta. 2 theta is just pi. So the conversions back to theta is not necessary. And when you do these substitutions, you will get pi over 8, which is the answers that you get from here as well. So I'm just saying that if you want to, you can still do all this thing. There's no problem. I will not stop you. You can still find antiderivative in terms of x. I'm just saying that for trigonometric substitution or any substitution that is complicated, you might not want to go all the way back to the antiderivative. You might want to just look at the corresponding substitutions and figure out what is the range for the corresponding substitutions. And you can just, like, without going all the way back for the for the definite integral, you can just do it like this. For the indefinite integral, of course, you will have no choice to find it, but to find the antiderivative, then it's just going to be a little bit more involved. So these are the two examples that we didn't have time to talk about in lecture. So make sure you understand all this, because you do run into questions or problems that looks like this in the web assignment. So I will see you tomorrow in class, and that's it.